All right, recording is rolling. Welcome to Tuesday, October 3rd. We're going to finish this rotational kinematic lab from yesterday. You guys still have the turntables on your desk, so if you want to follow along. Then I have some new posters and demos for you guys. This is going to lead into tomorrow's lab. I'll have you guys set up a table by the end of class today. Tomorrow, you guys are going to be determining what is centripetal force. What is that? How can you calculate it? Some kind of formula for that. Right. And so we're all working up to that point. So we got this turntable lab from yesterday. We're looking at rotational kinematic motion. Now, take a couple minutes here to do a review with you guys to get some new concepts you guys saw yesterday. Right. So we're looking at rotation in contrast to linear motion. Now, time is still time. Instead of saying how far in meters, now we're interested in how far something's rotated. There are different ways to measure that. You could do degrees or revolutions, but we're going to tend to stick to radians, especially if you're multiplying or dividing like directly in like some of these kinematic expressions. Okay? Got to have like radians per second squared. Right? If you try to put like degrees in here, it's completely nonsensical results, right? So radians is like the pure mathematical way to represent angles, right? Instead of v velocity for linear velocity, meters per second, miles per hour, we're going to do omega, like angular velocity. I might call that rotational velocity, like radians per second. How fast is it turning, right? Like the Earth turns at some rate, right? And then you could be like speeding up or slowing down, but like this turntable could be speeding up or slowing down, right? We're just interested in the top half of this table for now. We're gonna save the bottom half of this table for December time. Okay. There's a connection between how far something's rotated, this turntable's rotated, and say like how far a point on the outside is moved, like distance-wise, right? Just very simply multiply by the radial distance from the center, right? So if I got this outside Roosevelt, it's like driving around a huge circular racetrack, right? The odometer is adding up some total distance, right? Well, how far from the center is he? How far is this? He's gone around like radians-wise, right? See, if you're right in the middle, you're not going anywhere. So if you're 0 centimeters from the center, right, just everything zeroes out, right? You can also do how fast and acceleration, okay? Okay. Got these new kinematic expressions. These are the same three kinematic formulas that you guys had for linear, but just pop in the rotational equivalents. So how far in meters? Now we got how far it turns in radians and so on. Okay? So we're looking at all this with this lab right here. So I measured 15 centimeters out is this outside Roosevelt right here. Okay, so here's the center point. Here's 15 centimeters out. Focus on this guy. Okay? You guys might have some mass slugs on your desk. You can track that as you're rotating it. Okay? So this is a two-part story. Part one was 3 revolutions at a constant rate. Then you let it go. And part 2 was it slows down to a stop. Okay? So let's see if you guys remember. Guys, 1 revolution. How many degrees is that? 360 degrees. Okay. And how many radians is that? 6. So 2 pi radians is 1 revolution, right? Oh, okay. Kind of like circumference equals 2 pi r. It's kind of related to that, right? 2 guys did that yesterday, right? Right. So if you do 3 revolutions, right, say times 2 pi. Oh, that's where that 6 pi is coming from, right? So you did 6 pi radians, right? I timed mine with a stopwatch, got so many seconds it took to do that, therefore that many radians, that much time. Okay, it was rotating, assuming constant angular velocity was pretty close to, right? That many radians per second. Right? We also did, if you multiply by the radial distance, say 15 centimeters out, here's the total distance that Roosevelt was traveling, like 3 revolutions, right? Ooh, that's almost 3 meters. Ooh, that's a pretty good flip right there. And then here's like the linear speed, like if you point a radar gun at him or he's going through a speed gate, right? Notice I'm not saying velocity. I might say tangential velocity, right? But I have to be careful about just saying velocity because the direction's always changing, therefore the velocity is changing. Right? Kind of get towards a concept called centripetal acceleration that we're getting towards by the end of today, right? But not quite on this paper yet. Right? I did one more thing. After I let it go, after 3 rotations, I let it go and friction slowed it to a stop. I measured how far. Now every class worked out a little bit different. It looks like with you guys yesterday, it rotated a full revolution and then some after that. Because I know it's like 6.28 radians would be 2 pi radians would be 1 revolution, right? Looks like your guys' is, again, this always works out a little bit different. I did 3 revolutions and let it go, and then it spun by itself an additional revolution and more, right? And then some, right? So maybe you're measured in degrees with the protractor and then converted to radians. All right. We did some graphs. These graphs, we're just looking at the first half of the story, just when it was going at constant angular velocity. So this angular velocity is function time. Oh, look, there it is, constant, right? Okay, filled in the rest. Here's angular displacement as function time, and angular acceleration, of course, was 0 because while it was constant angular velocity, it wasn't speeding up or slowing down. Right, that's about where the bell rang. So we gotta finish this off here, finish out the rest of this. Right. So we're getting into the second half of the story. The second half of the story is the part where it's slowing down. Right. And here's what I know so far. I know it rotated the spar to come to stop, the spar in radians. Right. We gotta figure out everything else. This sounds definitely kinematic. I'm gonna make a kinematic checklist here. You guys remember tax VV? Right. These are the 5 kinematic variables we could be juggling. You know, those are the linear ones. Let's look at the rotational ones. All right, now time is still time, but here's angular acceleration, radians per second squared. Here's how far something could turn in radians. Right, we've been using theta to measure angles all along in this class, so that's most sensible. Okay. Right, angular velocity. Well, if it's changing, then maybe have beginning and end of an interval. Right. Okay. Let's put down on the board what I know. I know. Let's see, 7.59 radians to come to a stop. So that's right here, 7.59. That's radians. I'm not really interested in the linear stuff. It's just right there. So I got that. Right? Oh, guys, if it's slowing down to a stop, that right there tells you a number. What number do you know by saying slow down to a stop? Final angular velocity. Gotta call that 0 radians per second, right? So what it's breaking to, right? If only I knew one more kinematic variable, then this whole thing would be solvable. In fact, I do, because I remember this is how fast it was initially rotating. That's actually why I put the subscript not right here, right? Because it's like a lead into the second half of the story. Because I was rotating it pretty well at constant angular velocity at calculated 3.48 radians per second. Ooh, that is 3 kinematic values right there. Right? That means in principle, you can solve for the other 2. Right? In this case, what rate was it slowing down and how much time did it take to slow to a stop? Right? Right. So there might be different ways to go about this. Right, here, see what we have and what we don't have, right? We have these 3 guys. We don't know alpha or t, right? Which of these expressions looks most opportune to keep going forward? What do you guys think? First, second, or third? Say, if you don't know alpha or t, ooh, that's 2 unknowns there, and maybe we'll keep shopping for equations. Okay, so the same 2 unknowns there. Ooh, how about this third one? Right? This third one, we know everything except for the alpha. That's one equation, one unknown. That's probably the easiest way to do this, right? Just solve for alpha first using that third. Right? So I'm going to go final angular velocity squared equals initial angular velocity squared plus 2 alpha theta. Right? We're solving for alpha. What rate was it slowing down? Right? So I hope this is a negative number, maybe, right? Right. So you know what? Let's do this in terms of variables. Can you guys solve in terms of variables? Subtract this over, divide by the 2 and the theta. Okay. So omega final squared minus omega not squared equals 2 alpha we're solving for and the theta. Right. Divide these 2 coefficients over. So alpha is going to be this all divided by 2 theta. Right? See that? Right. You could have plugged in the numbers first. That'd be fine too. Good practice to be able to solve in terms of variables also. Well, omega final 0 anyway, so let's just get rid of that. Right, so it goes to 0. Right? So maybe just simplifies to that if it's slowing to a stop. Right? So alpha is, put some numbers, the negative. I got 3.48 radians per second. I'm going to square that value. Divide by 2 times 7.59 radians. Make sure you group all this in the together in a calculator, right? So it's all in the denominator. Otherwise, your calculator will not calculate that correctly. Okay, 2 by 7.9. Okay. So I'm getting negative 0.7977. Okay, I'm going to round that to negative 0.80 radians per second squared. It's pretty dang close to. Okay. So that's the rate that it was slowing down. It was losing 0.8 radians per second every passing second. Well, slowing down. Okay. That's another number on the table. Oh, I gave you guys a negative sign. So 0.80 radians per second squared. There you go. There's another one right there. Okay. We can also solve for time. Solve for time, right? Okay. So back to equation shopping. Now we have alpha. Which one looks like the easiest way to solve for time? Which equation are we going to use? First, second, or third? I like the second one also. Yeah, right. So the third one's totally out of the picture. We used it already anyway, and there's no time. Right? Could you use the first one? Yeah, but you'd run into what situation starts with a cube? quadratic, right? Okay, yeah, so I like your guys' suggestion to use the second one. That's probably the most straightforward one to use. Let's do that. Let's go omega final equals omega initial plus alpha times t. Now we should know everything except for the time, right? Could pop in numbers whenever you want. Maybe it's good practice to go ahead and solve in terms of variables. So practice over, divide by alpha, right? So alpha t is difference in angular velocities. Therefore, the time is difference in angular velocities, all divided by the alpha we just found, right? So let's pop it all and, okay, of course, this number is 0 rad per sec. Right, we're coming from 3.48 rad per sec. Right, this all was slowing down at a rate of negative 0.80 rad per sec squared. Just like that. Yep. All right, so that's 30.4. It looks like the negatives are going to cancel. Okay. I've got 4.35, and then the unit comes out to be seconds. Okay. All right, does that look reasonable? About 4.5 seconds. Yeah, if I had spinning pretty good and then let it go. Okay, yeah, 4.5 seconds it took the soda to stop. Right. That looks believable. That doesn't look crazy. So 4.35 seconds. Pop in right there. Right. Right, good spot. Right. I don't know why I put average on here. I'll come back to average later. Right. Let's make the graphs before we do average. Right. And let's get the linear values before we do the graphs, because probably have an idea how the. Right. So for the linear values, right? Now we're thinking about this like as a point traveling. Right? I'm thinking about, right, what distance did it take to come to a stop? Right. Again, like going around an arc. Notice I'm not saying displacement, because that's like as the crow flies, but I want to like add up like odometer of a car, like add up the whole trip, like distance, right? I also want to figure out, okay, yeah, okay. So first, right, distance. So couldn't you just take how far the turntable rotated in radians and multiply by the radial distance out? Right, that should give you how far it went, say in centimeters. Right, so let's do that. Got. So x equals theta r, right? You can call that arc length. A specific version of this you guys have probably known since like 5th grade is circumference equals 2 pi r. You guys know? Right, so I'm looking at here, 7.59 radians. Right. I meant to mention earlier, if you did this experiment yourself and you have your own numbers, your numbers don't have to match my numbers, but probably not crazy far off. Right? And my Roosevelt was 15 centimeters from the center. If you like, you can call it centimeters per radius, so this cancels, or yeah, radius is one of those like weird units. 7.59 times 15. Okay. I'm looking at, the number is 114 it rounds to, and the unit is centimeters. Ooh, all right. So that's over a meter. That's over a meter. Right? But I can kind of believe that, because this turntable here, this turntable is just a little bit smaller than that trundle wheel. You guys remember the trundle wheels? We were like blasting balls off the balcony. The trundle wheel. And that trundle wheel did have a circumference of 1 meter. Right? This one is a little smaller than that. Yeah. So yeah, over a meter it went. 114 centimeters. Yeah. So that looks like a believable number. Right? The other thing I want to know is, what rate was it slowing down? Like as if you were, imagine your little tiny car here, right? Maybe your little size, or like ant car. You're going around the track. You're going around, and you're slamming on the brake while you're going around. So you're slowing down, but like in a linear context, you're slowing down. Like ignore the fact that you're turning left continually, like so you're turning the steering wheel. That aside, right? Had you been like going in a straight line, I might call that tangential acceleration. Right? Oh, I actually put that subscript here. See, it says a tangential, right? Right. But we can get that by a tangential. It's just alpha times r, right? Right. So, similar idea here. Here, it's just the last one on this poster right here. Okay. So it was slowing down. I know the whole turntable was slowing down at 0.8 radians per second squared. It's negative because slow down. Right. 15 centimeters or centimeters per radius, if you like. Okay. Let's put it all together. Right. Looking at negative 12 centimeters per second squared, right? Because And this is a linear type concept. Okay? So it's be like as if you were smashing the brake in your car and you were losing, you were watching the speedometer needle move down 12 centimeters per second every passing second. Okay, so what's going on? The speedometer needle's moving down now, right? Okay. So something about the rate change of speed. Okay. Well, I gave you guys the negative sign. There's 12. So negative 12 centimeters per second squared. Okay. All right, you guys get that? All right. Let's finish these graphs. All right. I'll give you guys an opportunity. Right, so you can see them side by side. You can tell they're going to be the same graph shape, even though they're like different units. Okay, right? But what? How about like the angular ones at least, or what would this look like? Right, so the turntable slows to a stop. So go ahead, give you guys opportunity. I'm going to walk around the room and see who gets it. The turntable slows to a stop. Okay? What does that look like? The turntable slows to a stop. And you guys do theta, omega, and alpha versus t with the turntable slowing to a stop. Give you guys maybe a bit of a hint. It looks like Reese got theta versus t. This is kind of analogous in a linear sense to, okay, looks like Steven's got theta versus t, like a car braking to a stop. Okay? Because if you're in a car braking to a stop, if you're moving forward and you slam on the brake and the car's braking to a stop, are you still moving forward? Yeah, so you're still accumulating displacement. You're still moving forward, just at a slower and slower rate, right? Okay. So here we go. I'm going to start with the velocity one, angular velocity, and then branch out like I normally do on these. Okay, slow to a stop. What do you know about final angular velocity? Be zero, right? So in this case, 0 radians per second for this graph. Okay. If I look at my times, it was like about 5.5 seconds at a constant rate, and then about almost 4.5 seconds slow down. Okay, so maybe that's not exactly double T naught, but kind of get close to it, right? I'm trying to eyeball, get a pretty good idea for scale, like what would be reasonable, right? Okay, so slows to a stop. That looks like that one, right? Okay. Hey guys, what does the slope of velocity versus time tell you? What physical property does that represent? What's the rate change of velocity called in physics? Acceleration, okay? And since I see a constant slope, it's a constant negative slope. What does angular acceleration versus time look like? I think it's going to be just a constant negative value like that. Okay? In fact, I can tag a number to that. It's going to be negative 0.80. And the unit I embedded in the axis yesterday, radians per second squared, because we just found that right here, right? Now, if you're in a math class, they might make a big deal about like jumps and holes and the whole thing, right? In physics, you can either leave it like that, that's perfectly fine, or if you want to connect it, you could like connect it with these steep lines like that, right? That's okay too. It's up to you whether you want to connect them or not. AP will take either way. So if you connect it like this, or you just leave it like looking like a jump, AP will take either one, and I don't care. I don't care about like making a hole or anything. Okay, now maybe the trickiest one here is displacement versus time. Okay, so how to go in counterclockwise, we'll call it positive direction. Okay, so it's accumulating displacement, and then I let it go. Bam, right there at T naught, I let it go. Right, and it was still rotating, just slower, slower, slower. Yeah. Right. Yeah, there you go. Yeah, it's kind of like plateau, right? Okay. So maybe it'll like curve down like this, kind of bend down. Okay, and then what shape is that right there? Yeah.
Are you like asking?
You're gonna say a parabola, right? A parabola? Oh, yeah, parabola. Yeah, that's a piece of a parabola right there, isn't it? Okay. In fact, what we just did, the second half of the story, we're slowing to a stop. Where is it? Here it is. Okay. That's right there. That's one of these posters. You guys see a poster up here? It looks like that. Yeah, hanging in the room. Yeah. Turntable slows to a stop, right? So counterclockwise could be like positive direction, right? Okay, so if it's slowing to a stop, that means angular acceleration. Okay, I've got like clockwise, which would be the negative direction, right? Oh, you guys just drew those 3 graphs right there, right there, right? Just like that, right? Of course, they're related to each other, right? Like slopes, areas, the whole thing, right? Do you think if you scale each one of these by 15 centimeter radius or whatever size radius you use, you'll get the linear values for each one of these, right? So you guys know it's going to be the same basic graph shape, right? Like it's going to hook down like a parabola shape, right? Still moving forward, just slower, slower, right? This is going to velocity versus, or I should say tangential velocity versus time, or speed versus time. It's going to come down like this. And then the the linear tangential acceleration is going to also be a negative value. Right? Maybe we'll do one of each, right? So where I have one looking like a jump and the other like actually connected. Right? You could do either one. Right? It'd be fine. Okay. So side note here, I want to throw some definition type stuff at you guys while we're looking at these graphs, right? Because there's three type accelerations that we're juggling right now. Okay. So one on the bottom left is called angular acceleration. I might sometimes call that rotational acceleration. It has to do with the rate change of velocity of the turntable. So if the whole turntable like speeds up or slows down rotating, right? There's some associated angular acceleration that you can quantify, right? The bottom right graph, right? Something to do with like this guy braking to a stop as he's turning, right? Ignoring the turning bit, right? His speedometer needle is going down at some rate. Now that is a linear acceleration, but I'm going to call it a tangential acceleration. Right, so ignoring the steering wheel aspect, right? He's like slowing down, right? So I'm just saying like tangent to his motion, right? Just focus on that. It's like slowing down, right? Now there's a third kind of acceleration that's not specifically addressed like on these graphs or on this lab, but sort of related. And it's going to come back in like the next day or so. Right? It's something called centripetal acceleration. Centripetal acceleration. Right. Here, I'll at least say it's not shown in the graphs. Right. That's a third concept. That's the acceleration that has to do with changing direction. Right. Now, there is definitely changing direction going on here. Right? There's some kind of friction force that's holding this Roosevelt here, that's allowing it to make that turn in the first place. Right. That's causing some kind of inward force. Because absent that force, when it's in motion, it always wants to move in a straight line, like tangent to its motion, or tangent to its path. There's some friction that's always pulling it into a circle. That's forcing it like to pull into a circle. That's called a centripetal force. And if you divide by the mass of this Roosevelt, you get this associated centripetal acceleration, right? Which is not angular acceleration. It's not tangential acceleration. It's something a little bit different, right? It points towards the center. Right? Oh, yeah. Yeah, so angular acceleration is in radians per second squared. It has to do with the rate this whole turntable is slowing down. In fact, all three of these Roosevelts have the exact same angular acceleration. They're all slowing down at the same rate, like in terms of like degrees per second squared or radians per second squared, right? But they all have different linear accelerations. Like if they were all in a race, suppose you got three independent cars, right? And maybe it's not even a turntable, maybe just watch them race around. This guy's parked, right? This guy is like putting around a circular racetrack, and this guy has like, right? But maybe their motion also looks like this. They all slam on the brakes, right? So they're all slow into a stop, right? Now, braking, that's something you can definitely feel inside a car, right? Right? Who feels a greater braking force? The guy on the inside or the guy on the outside? Definitely the guy on the outside. I bet he feels like twice the braking force of this guy because he's like twice as far out, right? And that's related to this poster here. Okay. That's like this right here. So angular acceleration is the rate that the whole turntable is slowing, right? Which is the same regardless of where you're standing on the turntable. Right? But the further out you are, the more you're slowing down, like in a linear sense, right? So if you were watching the speedometer needle in your car go down, right? That's what that is. Yeah. Okay. Right. That's like centimeters per second squared or meters per second squared, something like that. Okay. Right, basically. Okay. Let's knock out these average values real fast. You can get that off the graph real fast because just during the slowdown bit, I'm just interested in the slowdown part. Right? Wouldn't average angular velocity be like halfway down here? What is 3.48 divided by 2? Right, that's like 1.74. Right, again, that's just while it's slowing down to 1.74. Right, and the linear velocity, well, half of 52 is 26. That'd be centimeters per second. Or take that, multiply by r, Jane, get about 26.1, 26, okay, that's somewhere there, right? Centimeters per second, okay? If you do average velocity times time, you get the displacement during that interval. Okay, it's a little bit different way to think about it there, okay? Guys, good? All right, so this page, let's do this. Just as you guys are walking out the door today or right before you walk out, go ahead and turn this into the gray tray. Make sure your name's on it. I will get that graded, put points in the grade book, and get this back to you guys pretty soon because there's a different lab on the back that we'll do another day. Okay. Anytime, rest of class today, I got new stuff for you guys, new posters, demos that are going to lead into this next lab that we're going to be doing. Okay. So, here, let's start with some posters here. Now, here, let me do things a little out of order. Okay. Let's do this cup. Let's do this cup first. A cup of water. So I got a cup with a string on it. What's this about? Let's do this cup on the string. Okay. So put some water in it. I got water in this cup. Water in a cup with a string. Okay. Hey, how can I turn this cup upside down and the water doesn't fall out? How can I do that? Spin it in a vertical circle, right? You put it in motion. Right? So if you're watching this video, I have to do this off camera, right? But imagine I'm going to spin this in a vertical circle. That's what I'm going to do right here. Okay, here we go. Oh, look at that. Like right here, the cup is upside down, but the water's not falling out. Imagine if you're a goldfish thrown around, right? You might feel like you're thrown towards the outside, but from your guys' point of view and your desk, you guys are in an inertial frame of reference versus the goldfish thrown around in this water here is in a rotating frame of reference. Right? So you experience different things. You guys see that there actually is no force that's ever pushing the goldfish out. What there is the goldfish is always trying to do tangent tooth motion, Newton's first law of motion. And the bottom of the cup is always forcing the goldfish into a circle, right? So there's only ever an inward force from the bottom of the cup, right? Now, if this is going too slow, do you think at some point the water would fall out of the cup if it's going too slow? So there might be like some minimum speed it has to go, right? And I bet that is probably related to maybe like the length of the string, maybe the radial size of that circle, the radial size of curvatures that's going around. Right? And maybe something else to do with Earth gravity strength, right? Like if you did that on the moon, maybe it doesn't have to spin as fast to stay in the water, right? So hold on to that idea because that's a part of a setup for your guys' lab tomorrow. Hold on to that idea. That's come back later today. Okay. It's related to the O'Neill cylinder. Okay. But I got some other demos for you guys. Got some video demos, but I got the poster version. So let's look at the poster version before I switch my screen over. Okay. Now let's do focal pendulum first. Right, focal pendulum. Okay. So, like in this room, what evidence can we have, like in this very room, that we are on a giant rotating planet? Now that's a really tough one, right? If you go back 2,000 years ago, people saw some kind of rotational motion. If you ask someone 10,000 years ago with geometry of everything, they'd say, okay, well, it looks like everything's going around us. I see the moon going around us, and it looks like the sun's doing a similar type thing, and the stars, and maybe the Earth is the center of everything, and everything's moving around us. Right? Nowadays, you're taught something much more accurate, which is, actually, the moon's going around us, sure, but the Earth goes around the sun, right? Sun is like a stationary solar system, more or less, right? And what evidence do we even have that the Earth is spinning, right? Okay, you see the sun like rise and set, true, but again, how do you distinguish that from like the sun orbiting us, right? Which definitely isn't, right? So here's this focal pendulum. You could actually have this experiment, say, in this room in principle, and you could prove that we are on a spinning planet. Okay? If you get a pendulum swinging back and forth, Newton's first law of motion, it just wants to travel just in a straight line, just back and forth all day. Right? Now, how can you get rid of like air drag, frictional losses? Well, you can put a little motor up here just to add a little bit of energy, just a little hit, right? Like someone on a swing, right? Which doesn't really change direction of motion, just adds the energy that would have been deleted from like air drag. Right? And so it just keeps going back and forth, back and forth, back and forth. Right? And the Earth actually spins underneath it. So that could be evidence that you're actually on a rotating system, right? You're in a rotating frame of reference. Right? Now, what would that look like from the surface of the planet? Right? That would look like the pendulum itself was changing its angle over the course of the day, even though it isn't. The pendulum is just going back and forth, and it's the Earth that's actually rotating underneath it. Right? You guys get it? Right. So I've got some videos of that lined up. Right. On here, talk about this Coriolis effect too. Ooh, this one's fun. Okay. So here's more evidence that we are on a spinning planet. Okay. We've got this globe demo. I'm gonna have to do this off screen. It doesn't really fit for the video, but if you're watching this video, then use your imagination. Right? I'm gonna point my finger and then like trace a line straight down like this arc. Okay? So suppose we're up here at the North Pole, and it's Christmas time, and we're Santa Claus, and it's time to blast the presents. We're like, oh ho ho, pow pow pow. We're just like Santa cannon break out, blasting these presents. They're going down the chimneys. That's how he does that, right? Right? So if I follow just straight down, let's follow this present. Pow, ho ho ho. It goes like straight down, right? Straight south, straight south. Right? Now if the planet's not spinning, it'll just go straight south. Okay, no problem. Right? But we're on a spinning planet, right? So if you add some spin to it, ooh, ooh. Now my finger's just going straight south, but with the rotating Earth underneath it, what does it look like the president's doing from Stanley's point of view? Looks like it's curving off to the right. Interesting, right? Right. What about like if you're down here in the South Pole? You got this. The Earth rotates. Does it go this way, right? Okay, so say there's like some pink one we're in Antarctica, and we start blasting cannonballs straight north. Ooh, that looks like it's curving which way? Kind of to the left, even though it's just following an arc straight north, but the Earth is turning underneath it. Right, so you get this type of rotation motion too. There's some stories this is kind of disputed, so it's not 100% confirmed historical. That when cannons got powerful enough, people started to possibly notice this effect. Right, if you blasted a cannonball, like several hundred meters, you might tend to consistently miss your target, and it would tend to kind of veer off to the east. Most wars are like in the northern hemisphere, right? Something like that. What's going to explain this? Well, remember, there's two kind of velocity now going on, as of yesterday, right? You got linear velocity and you got angular velocity. Now, no matter where you're standing on Earth, everybody has the same angular velocity, this omega, right? Everybody has the same turns per time. You can call that one revolution every 24 hours on the Earth, right? You could convert that to some radians per second. I think we did that yesterday too, right? But depending on your latitude, you can have a wildly different linear velocity relative to the axis of the Earth, right? I'm ignoring the Earth revolving around the sun, which might have a tiny effect too, right? But just the Earth spinning itself, right? If you're standing on the North Pole, relative to the spin of the Earth, you have zero linear velocity. If you're down on the equator, you're moving like 1,000 miles an hour to the east, or pretty close to, right? So if you change your latitude, then you're going from a latitude where you have one eastward velocity to a different latitude where you have a different eastward velocity, right? And the ground is like shifting beneath you, right? Now, it could be a really subtle effect. It's really hard to tell unless you have a pretty significant change of latitude, right? So, but there's different examples of this, like find out like having a real effect, right? One classic example is hurricanes. Guys, hurricanes, are those high pressure or low pressure systems? Low pressure. That's like, you see a big old L on a meteorological map? It's low pressure, right? You guys think that all this air mass wants to fill that void like a vacuum, like and sucked in, right? But if you're changing significant latitude, right? Whether you're blasting from the north-south or south-north, as long as you're in the northern hemisphere, I think it's kind of tend to veer off to the right. Now, it's not really veering off to the right. It's just going in a straight line. The ground underneath is shifting to the left, right? But, right. So, okay, and if you pay close attention, every hurricane you see passing over the surface of the Earth, right, always has this counterclockwise motion. Oh, hey, look, it's lined up right there. Counterclockwise motion, right? Now, if you go down south like Australia and see like a cyclone there, that one's going clockwise, but this one's going counterclockwise. And all hurricanes passing over Florida go counterclockwise. Right? Most tornadoes also go counterclockwise, but those are small enough systems. Sometimes you get some backwards tornadoes, right? So got that. Right. Since I'm talking about Coriolis effect here, this Coriolis effect, let's look at where's Coriolis? Here it is. Right. Let's watch these. Here you go. Kids on a merry-go-round. So we're up in a helicopter looking down. Let's go back to the beginning there. Right. And do you guys see that yellow ball? If I hold a meter stick up to the screen, that yellow ball only goes in a straight line. That's a straight line path. That's a straight line path. Right? But if you're on the if you're inside that rotating frame of reference, it looks like it's all going like curvy wackadoodle, right? So from that ball is going in a straight line, right? That ball is straight line, straight line, straight line, right? But you wouldn't know it inside the rotating frame of reference. And sometimes it's hard to tell if you're in a rotating frame of reference, right? Especially if it's big enough, right? That helicopter point of view, you could call an inertial frame of reference because it's non-accelerating, right? But those kids on the platform, they are in a rotating frame of reference, which is a type of acceleration. It's called centripetal acceleration. It has to do with like changing direction because they're always like changing the direction, right? So there's a Coriolis effect there. All right, let me pull up my Foucault pendulum. Right, so, yeah, go ahead. Yeah. Right, yeah, because the ball and you and the Earth are all traveling like together. Right? Yes, throw the ball up and it just comes straight back down. Right? Yeah.
will keep going, or like still, it won't just come straight back to your hand.
Okay. Well, if you're like changing latitudes, yeah, then it would like curve off to the right. Like I know like airplane pilots have to kind of worry about that if they're going straight north or south, right? They might veer off a little bit. There's an effect like I know if like you have a big cargo ship and it's traveling east versus west, it actually weighs a little bit differently because of that. Um, yeah, so it'd be like a subtle effect unless you're like going like significantly fast east or west or changing latitude north south.
It's not going to like rotate around.
Are you talking about the kids on the merry-go-round?
Yeah.
Oh.
Cross it up. Go on a straight line out.
Right. Or okay. Yeah. Right. True. So from this inertial frame reference, yeah, the ball always just travel in a straight line. Yeah. Yeah. And then on the platform, it looks all crazy. Yeah. So it's weird. Kind of hard to describe, right? Okay. Um. All right. Okay. So a lot of science museums like have these pretty cool. I know some universities around here. If you guys go to UCF over in Orlando or USF over in Canada, go to a little scavenger hunt. You can find one of these flip cup windows. Oh, they're starting to bump that head. You guys see all these guys knocked down, right? Now, this works really well the closer you get to the poles. Let's see, is this one that knocks it over? Ooh, maybe it's the next one. Right? If you're on the North Pole, this would go all the way around once every day. If you're on the equator, this would be like a terrible demo to have as a science demo. There, knocked over, right? Because it would just go back and forth and it'll look really boring, unless you wanted just to show that, right? Let's do a time lapse version of this, time lapse, right? And see that looks like it's kind of veering clockwise over the course of this video, right? Again, actually what's going on is just going straight line. The Earth underneath it is the one that's turning, right? This can tell you something about the spin of the Earth or like which hemisphere you're in, or I guess kind of both, right? Which hemisphere you're in, that can tell you. Here, you can tell that you're in the northern hemisphere because how that's rotating, right? Okay. All right. All right, let's get closer to I had that water in that cup and I was spinning that around, right? Let's get closer to that concept. You bring in centrifugal force. I'll talk about that. So you guys remember like centrifuge? If you're sitting inside one of those boxes, the rotating frame of reference, but it might be kind of hard to tell that it's a rotating frame of reference, especially if it's big enough radius. Did I show you guys the 9G guy? You guys remember 9G guy? So sitting in one Earth gravity there. He's sitting inside the centrifuge. They spin him up to like 9Gs. Right? So he feels some kind of force. Now, he thinks that there's a force throwing him outwards towards the back wall. But really what's going on is that he's trying to travel in a straight line according to Newton's first law of motion, and the back wall is pushing him in, right? That's what's really going on. But if he doesn't know he's in a rotating frame reference, it's really hard to distinguish the difference, right? But there is no outward force on him, right? Now, maybe he's putting an equal and opposite outward force on the wall, but there's no outward force on him. There's an inward force from the wall that's pulling him in and calling it a centripetal force. Right now, if you're up in space, okay, now you're 0G, unless, hey, maybe if you have like a rotating frame of reference, right, you might experience some artificial gravity, right? Do you guys think you could be like walking around on the outside or like the inside wall here, right? Walking around, right? And if it's rotating, that might feel like an artificial gravity field. This is from a movie in 1960s called 2001: Space Odyssey. Do you guys think if you wanted to target an artificial gravity of like 9.8 meters per second squared, and you knew the radial size of this, like, oh, so many meters radius, you could calculate how fast you have to spin that, right? You could quantify that in some radians per second. Ooh, right? Or point out on the edge, if you point a radar gun at it, you could get how many meters per second it's moving, right? What does that look like on the inside type, right? Now, of course, this is all special effects. This is just a movie. I think it made like a giant hamster wheel and they're just like spinning on the ground, right? But if it was up in space, right, this is kind of what it would look like, right, sort of, right? Actually, this one's kind of small for that too. The bigger it is, the better it is because it's hard to tell that you're actually rotating. Right? Physics get really wonky on like small rotating spaces, right? But it look kind of like this, right? Again, that guy thinks that there's a gravity field pulling him out, right? But really, what's going on is he's always trying to travel in a straight line, but it's that wall that's pushing him in, that's providing a normal force, right? That normal force is acting as a centripetal force, right? And this is going to lead right into the next lab. The next lab I have for you guys, we need to somehow quantify what is this centripetal force. What is this centripetal force? Straight on the camera here. Here. Okay. Right, so you guys got either paper or your lab notebooks. Lab notebook, or if you have a lab, and some of you guys use the lab notebooks. If you don't, here, like there's some paper here. If you want to use some paper, right? It's up to you. Lab notebooks or paper, because I'm going to have you guys draw a table here in the last few minutes of class. Right, so while you guys are getting those out, make sure you guys are set up for tomorrow. Tomorrow, I'm going to give you guys some PVC pipes, some string, and a couple of Play-Doh canisters. This is what this looks like right here. Right, PVC pipes, some string, and a couple of Play-Doh canisters. Right. The Play-Doh canisters, you can pop them open, and oh, look at that. It's a little mass slug. Pop that in, close that. Right. Now, these are different masses, different weights. Ooh, this pink one feels pretty heavy. This green one feels pretty light. Right. What I'm going to do is off camera, so use your imagination if you're watching the video, right? So I'm going to spin it like this. I'm going to spin the green one, and the pink one I'm going to let it hold down. Now, the pink one down here is going to be in static equilibrium. It's not going to be moving up or down. And the green one is going to be on the circle of constant radius. Let's see what that looks like. Okay, so right here. Look at that. Yeah. Now I have to spin it at just the right speed to maintain a certain radial size. Okay? If I spin it too slow, oh look, see how the radius gets smaller and the pink one falls down. Okay, if I spin it like faster, that radial size opens up and the pink one kind of drifts up. But then if I like maintain it at that speed, then I can maintain that radial size. Okay, right now this lab, this one of these labs that if you're really meticulous about like keeping a constant radius per trial and this sort of thing, the data can come out really nice and you can really show this equation at the end. Okay? This is also one of those labs that if you're kind of sloppy about like maintaining this radial size or collecting the data, the graphs can be really messy and all over the place. Right. So how good these graphs come out really depends on how good you guys are at like really collecting this data, maintaining this radial size. Hold on, right? Okay, so I've got here 4 variables that I'm juggling. Right? I've got the weight of the one that's hanging. Now I didn't draw the full free body diagram, but the tension is pulling up, isn't it? And you guys think the tension is actually pulling this top mass into a circle, right? Because if you cut the string, you want to fly off a straight line. But it's being pulled in by the tension. That's called a centripetal force. That's a force that's not changing its speed, but it is changing its velocity because it's changing the direction of motion, right? So, into that circle, right? Okay. So this weight down here, this hanging weight, is effectively the centripetal force, isn't it? Right? I mean, it's the tension, but it's equivalent to that, right? There's some radial size that probably matters, right? There's the mass of this guy that's being pulled into a circle matters, and also the speed. You could also call it tangential velocity, right? The speed or the tangential velocity. Right? Let's make a table. This table is going to be 11 columns. Go ahead and put your name, or if you have a lab notebook, your name's on it. Right? We need an 11 column table, 11 columns. The paper itself is 11 inches wide. Maybe each column's a little bit less than an inch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, right there. Okay. All right, so we're gonna have make another row right here. Right, just need variables and units. Right, so we're gonna have different trials going on. Right, and we're gonna have different units attached for these different variables. Right? So trial maybe 1, 2, 3, 4, 5, 6, 7. Right? You guys have done enough labs right now. You guys know the more data you gather, like the more telling your graphs are going to be, right? Right. So let's go. What kind of data could we collect? Right. Maybe what is the mass of the hanging canister? Let's say grams. I know kilograms is the base SI unit for mass, but I really care about proportional relationships for this lab. Right? Let's go grams, little tiny grams. Right. Now, I don't really care so much about the mass that's hanging. I care a lot about the weight that's hanging, right? The weight hanging, because that's like the downward force, right? Going from mass in grams to weight in millinewtons, just multiplied by 10 meters per second squared, this is going to be millinewtons. Millinewtons could be. Right? another variable we have on the board is the mass that's swinging. And if I ever just say mass out of context for this lab, I'm probably talking about the one that's swinging because I care about that mass. That could be in just grams. Let's do 1 over the mass, 1 over grams. That may or may not be relevant depending on what setup we got. Okay. I care about the radius. That could be in meters or centimeters. Maybe we'll call it like centimeters, for example. Right. Right. Let's do 1 over r. That might be relevant. 1 over centimeters, something like that. Okay. And then I got some more columns that are going to be related to the speed of this thing, the speed of this thing. Okay. So, sure, guys said, now, I'm going to finish out this table too, but we'll have to do the beginning of class tomorrow. Remind you guys how it's going together. But I want you guys to see this big picture concept before you walk out today. Okay? So these 4 variables that we're juggling. Well, the only way to make sense of this, or the best way to make sense of this, is to have 3 independent experiments and then to bring them all back together at the end. Right? So you should see a card. Do you guys see a card taped to your desk? Right? It's one of these 4 suits. So depending on which suit you have, I'll put you in one of these experimental groups. If you have the spades, I want you to say, what's this speed, like this this balancing speed, as a function of the swinging mass. So you're changing out different swinging masses. But if you do that, you're controlling for the hanging weight. So that one stays the same. And also the radial size. So if you have like 40 centimeters radius, make sure it's 40 centimeters for the entire day tomorrow. Right? If you have the diamonds, then change out the hanging weight and let everybody's relating everything to speed. But you're leaving the top mass the same, and you're also leaving the radius the same. So like 40 centimeters for the whole day tomorrow. Okay? If you have the clubs, then what I want you to do is leave the canisters themselves closed for the entire lab tomorrow, but change out this radius. Maybe do like 20 centimeters, 30, 40, 50, 60, 70 centimeters, right? So how does that affect? If you have the parts, let's treat that as a wild card. So you can just pick one of the above and see what happens from that, right? And what we'll be able to do is bring all together into like one master function that can tell you centripetal force as a function of M, B, and R. All right, so wrap on today. All right, you guys have a great afternoon. Oh yeah, turn your labs, turn kinematic motion lab. All right, and I'll see you guys tomorrow.